Hello everyone, my name is Zhengye Han, and I am a first-year PhD student from the Department of Electrical and Computer Engineering at New York University. Today, I will present our paper, A Mathematical Programming Approach to Computing and Learning Berk-Nash Equilibria in Infinite Horizon MDPs. And this is joint work with my advisor, Quanyan. We are very glad to share our work at GameNets. Now let's get started. Let's look at the core problem of our research. In complex networks, agents cannot optimize against objective reality. They optimize within their subjective models. Look at the picture on the left. This represents the objective reality. It is a massive, highly complex system. In the real world, an agent simply doesn't have the power to know all this information. Because of this, they have to rely on what you see on the right, a subjective model. It is a heavily restricted and simplified version of the world. They use it because it is computationally tractable. But this creates a gap. How do they use this simple model to survive in that complex reality? Let's move to the next slide. How can an agent learn and optimize using a restricted, potentially misspecified model? As you can see in the picture, the process is a closed loop. At the top, the agent makes decisions based on its misspecified model. That simple box. These actions are then executed in the true environment at the bottom. The environment reacts and generates new data. Finally, the agent uses this data to update its model, and the cycle continues. But there are also some challenges. For example, can this loop eventually reach a stable, self-sustaining state? To answer this, we build on three key pillars of existing literature. First, the Berk-Nash Equilibria. As the slide shows, in this framework, agents behave optimally given constrained subjective models that statistically match observed data. Second, we use tools from regularized MDPs. Specifically, entropy regularization ensures its policy uniqueness and tracks both these points computation. Third, we draw on conjecture online learning. Here, non-stochastic bandit algorithms enable adaptive model selection under cognitive constraints. So, building on these foundations, how do we formulate our problem? The first step is to create a modeling framework that decouples the objective reality from the agent's subjective model. In other words, we need mathematical tools to separate what is actually happening from what the agent thinks is happening. First, let's define objective reality. Remember, this is unknown to the agent. What we model this as a standard Markov decision process, denoted as M2. It has the standard components you are familiar with. X is the state space, A is the action space, R is the reward, and beta is the discount factor. But here is the most important part, marked in the red at the bottom. The agent does not know the true transition probabilities, P. As you can see in the graph on the right, when moving from states x0 to x1 or x2, the true transition rules P1 and P2 are basically question marks to the agent. So what does the agent do? It uses subjective model. This is another MDP denoted as NSUB. The states, actions, rewards, and discount factor are exactly the same as the real world. However, look at the blue text at the bottom. Instead of the unknown P, the agent reasons using a parameter family of Markov kernels, denoted as Q theta. In the graph, the agent believes the transition happens according to Q1 and Q2. And notice that the true kernel P does not necessarily belong to this family Q. Here, we put them side by side. On the left, the objective reality in red. On the right, the subjective model in blue. This brings us to a very natural question at the bottom of the slide. What is the agent trying to achieve in this mismatched world? Let's look at the answer on the next slide. To answer this, we define our core objectives, the goals, which we define as the Berk-Nash solution. It consists of two conditions. Condition 1 is subjective optimality. The agent acts optimally relative to its own subjective belief. In other words, given a belief, what is the best policy? Condition 2 is statistical consistency. The agent's belief minimizes the gap between its subjective predictions and objective reality. Meaning, given the actual data, what is the best belief? Now, let's put these two goals together into what we call the learning loop. Let's walk through the cycle, starting from the top. At the top, the agent starts with some subjective beliefs. And following the arrow to the right, based on this belief, the agent computes an optimal strategy, pi. The step is exactly what we call subjective optimality. Following the arrow down, the agent executes this strategy, which interacts with the real world and generates the objective reality. And following the arrow to the left, the agent uses these observations to update beliefs, trying to minimize the gap. Third step is the statistical consistency. And this is our philosophy to summarize the entire circle. Beliefs shapes actions, actions shapes observations, and observations reshape beliefs. This loop makes perfect sense conceptually, but how to do this mathematically? How exactly do we compute this strategy and update this belief? Let's break down these equations. First, let's look at subjective optimality. Since we are in an infinity horizon setting, we must answer a basic question: why infinity works? In the middle, you see the formula for the expected infinite horizon cumulated returns under the subjective model Q. The secret to making this work is the discount factor, beta. Look at the two graphs below. On the left, without beta, the sum of infinite rewards explodes to infinity. It becomes computationally impossible. But on the right, with beta, between 0 and 1, the infinite series converges, making V computable. And this gives our agent a clear, finite target to optimize. Now the target is computable. How does the agent find the best policy? That brings us the best response. To find the maximum return, we use the standard Bellman equation for the associated optimal value function V. Based on this, we can define our optimal strategy. Given theta, a stationary policy pi is a best response to theta if for all states x, the policy only picks actions that achieve this maximum value. We collect all these optimal policies into a set. As you can see in red at the bottom, the best response correspondence is BR, which includes all policies pi that are a best response under Q theta. So this takes care of subtractive optimality. But what about statistical consistency? Let's move to the next slide. How do we measure the gap between the agent's belief and reality? We use long-run KL divergence. First, when an agent executes a policy in the real world and we divide the induced Markov kernel, suppose that P admits a unique stationary distribution. Then we use the long-run KL divergence equations to measure the mathematical distance between the agent's subjective predictions and this true steady state. Therefore, the conclusion is at the bottom. A subjective parameter theta is statistically consistent if it best approximates the true transition kernel in the KL sense. In short, it's the closest guess that the agent can possibly make. Finally, we bring the math and the conceptual loop together. This is our infinite horizon Berk-Nash solution. Look at the red equations we just added into the loop. On the right, subtractive optimality, the policy pi star must belong to the best response set of belief theta star. And on the left, statistical consistency, the belief theta star must minimize the KL divergence given the data generated by the policy pi star. It's a system where each side depends on the other. When both conditions are satisfied at the exact same time, the loop stabilizes. We have reached what is written at the bottom, a mutually self-sustaining fixed point. So we have a beautiful self-sustaining loop. The equilibrium is elegant in theory, but how do we actually compute this loop? Let's translate the theory into a computable algorithm. To compute the optimal strategy, we look at the problem from two perspectives, the primal and the dual. On the left, we have the primal optimizing value. Here, the linear program minimizes an upper bound function, v. By finding the tightest upper bound, it exactly recovers the maximum achievable value. As for the dual optimizing flow, the dual perspective makes a brilliant shift. Instead of values, it shifts the decision of variables to the discounted occupation measure, denoted as eta. So why is this powerful? Because searching directly over policies pi is highly nonlinear and hard to compute. The dual problem allows us to optimize over a tractable linear flow eta. Once we solve for this flow eta, the optimal policy is simply the normalized float. So if we put these two places together, the dual linear program, which handles subtractive optimality, plus the KL minimization, which handles statistical consistency, we arrive at our computational framework, the Berk-Nash bilevel program, BNBP. Let's look at how this bilevel structure actually works. A bilevel program is an optimization problem and nested inside another. We separate the agent's text into two distinct layers. Now look at the left side, the upper level, which is objective learning. While the agent is busy acting, this higher level evaluates the results and finds the parameter theta that minimize the KL divergence. It updates the belief. As for the right side, the lower level, which is subtractive acting. This is the dual LP we just discussed. It simply means the agent maximizes its subtractive reward under its current mental model, Q theta. The beauty here is the separation of concerns. The lower level acts and the upper level updates beliefs. And once this bilevel system is solved, the optimal flow, eta star, maps directly back to our equilibrium policy, completing the entire process. However, computing this bilevel program is not easy. The challenge is non-smoothness. The lower level LP strictly favors deterministic greedy policies, so the set of optimal solution of lower level S may be a non-smooth correspondence. And then the upper level objective KL divergence becomes non-differentiable. So how do we fix this? Then we can talk about the fix. Entropy regularized subtractive MDP. Look at the modified reward function. Instead of just the standard reward, we introduce an entropy term weighted by lambda. This small mathematical addition changes everything. By our theorem, there exists a unique entropy regularized subtractive value function. By injecting entropy regularization, the lower level best response becomes uniquely determined and smooth. The mapping from theta to subtractive model Q to discounted occupation measure eta to policy pi is now strictly continuous. Of course, the lower level is uniquely determined and smooth. The nested bilevel program collapses into a single level objective. Finding the regularized Berk-Nash equilibrium simply means solving the term at the bottom. Now, we have our framework. How does the agent learn over time? We use online learning via EXP3. First, look at the formulation. When the parameter space is finite, we cast model selection as an adversarial multi-R bandit problem. In this setting, the R's are the models. Each parameter, theta k, is an R with a dynamic loss. To manage these R's, the agent uses the weight. It maintains a weight WK for each model to track which one performs best. The process follows 4 steps. Step 1 is sample belief, theta t, based on the current weight. Step 2, compute optimal policy pi for that model. Step 3, execute policy and observe empirical KL loss from the environment. And finally, step 4 exponentially updates the weight. This adjusts our trust in each model based on the new data. Let's see this in practice. The slide shows our numerical validation, EXP3 in action. Look at the picture on the left. The x-axis is time, and the y-axis is the probability of choosing a specific model. The algorithm successfully identifies the least misspecified model, theta 1, selecting it nearly 82% of the time. And the picture on the right, the running average loss smoothly converges to the theoretical lower bound. Next, we examine the sensitivity to entropy regularization, specifically how the temperature parameter lambda shapes the equilibrium. Let's look at the left graph, which shows the value function. As lambda approaches 0, the policy transitions from pure exploration to sharp deterministic choices. At the right graph for the optimal policy, as lambda approaches 0, the value smoothly decrease and stabilize to the true Berk-Nash equilibrium. Up until now, we have still a finite number of models, but what if the parameters space is continuous? So this is the challenge. A fixed grid works for discrete spaces, but for continuous parameters, a dense grid leads to the curse of dimensionality. To solve this, we introduce the solution, the zooming mechanism. Here is how it works. The base algorithm is to run standard exp3 to balance exploration and exploitations. And the trigger is every t zoom steps. Pause and evaluate the set. When we pause, we do two things. Step 1 is pruning or discarding. We remove parameters within high estimated loss because they are suboptimal. And we remove parameters that are already highly certain because they have converged. We don't need to explore them anymore. Step 2 is refinement or zooming in. We identify active uncertain parameters with low loss, and then we generate a high resolution grid strictly across these promising candidates. Instead of searching everywhere, we only zoom in what matters. Let's see how this performs. The slide shows dynamic zooming finding the true peak. Look at the left graph first. This is the parameter selection. As you can see, initially exploring a wide range, the algorithm rapidly concentrates near the true model. You also see some dots scattered above. These occasional spikes reflect necessary exploration. Now look at the right graph. This is the corresponding loss, while exploratory pools cause momentary spikes. The running average steadily converges to a low value. This perfectly confirms that the zooming mechanism effectively isolates the minimal loss region. This brings us to the end of this presentation. Let's quickly review what we have achieved. In summary, we made 3 main conclusions. First, a unified framework. We established a rigorous mathematical programming approach for the infinite horizon Berk-Nash equilibrium under misspecification. Second, making a tractable file entropy. We resolve inherent non-smoothness using entropy regularization, creating a continuous and solvable objective. And third, scalable online learning. We designed the adaptive exp3 algorithm with a zooming mechanism, achieving high precision while beating the curse of dimensionality. And looking ahead, there are very exciting directions for future work. We can look into multi-agent network games to extend this framework to distributed sensor networks. And also we can study misspecification propagation to investigate how localized errors propagate through complex network topologies. Okay, thank you all very much for your time and attention. If you have any question, you can contact me via this email address. Thank you.